Alright, hit the button. See if it works. Yeah, okay. Couldn't get it to load YouTube. It almost looked like it was blocking me from streaming. But it appears to be okay. Alright, so it's always something, right? It's not always something, but yeah, I'm going to say that anyway. Even though it's not always something. Anyway, so yes, we have a video to respond to, so we will respond to it as we promised. An appropriate, presumably, response video that is on the subject of physics, not on some other bullshit subject, not full of a bunch of accusations and insults, and all of that crap. So, Aleska fellow made a video, and so far so good. It seems, I don't think he can make these arguments. What Newton said, I think we already read that, but okay. You want to try to make Newton into a free willer, you can go ahead. I mean, you want to try to say he believed in Leibnizian nonsense, you can go ahead. Leibniz published his theory before Newton, so it was before Newton made it kind of clear it's a 9.8 meters per second force. So, which kind of closes the door on all of this anyway. But anyway, we'll get to that. I was going to make a video where I just say, look, I'm just going to go over these points in every video over and over again until somebody addresses them. So we'll see what he exactly addresses. Alright, so let's see if it's still streaming. Alright, well, okay, so there's a stupid interruption in the middle of the video. Yeah, maybe I should just start over. I think I will. Should I or shouldn't I? Oh, let's just get on with it. Let's see if it'll work this time. Maybe it'll crash again, then we'll start over. Maybe I should check and see how much disk space there is. Maybe that's an issue of some kind. There's still enough. So let me just delete some crap just in case that's a problem. And such. Alright, well, whatever. I don't know why it fucktarded, but it did. So, alright. I'll assume it's working. And I guess I'll have to reload the chat, because that usually doesn't work. So somebody in the chat could just, if there is somebody, you could just say something so I know the damn thing's working. The video's streaming appropriately. Or not. It doesn't really matter. Yeah, who cares? We'll find out, won't we? Okay, the sound looks okay. I'm just going to assume it's okay. Now let me see if I can get Firefox to work this time without it blowing up. As that was really irritating. Alright, live streaming. So that's where I am. So that should be this. And it appears to be working. Okay, so now we'll go find the video. It's always something. As stated, it's always something. Alright, so here's the video. So we'll get that better centered and be on with the show. So we'll have full volume there. Might have to turn this. No, it's probably okay. Alright, so let's begin.
Okay, I'm making this video to address some of the points you, Gary, have made on your DraftScience channel. I will be talking about what Newton actually said, or at least what is the correct interpretation of Newton's second law. Something about guns and bullets.
Whatever. I don't know what that means. The correct interpretation of Newton's law. You're. I mean, it's just. That's what's at debate here, I suppose. So, but anyway, go ahead.
And finally, something about acceleration and fuel consumption.
Yes, which will be nonsense. Again, this is such an old and tired argument. I mean, I was just thinking about the Ian Gosling has a treadmill. Well, just put you can just get these people. I'm sure he has one. These devices that measure how many amps are going into a device when you're running it. And put it on 1 speed and then put it on twice the speed and see if it uses 4 times the electricity. I mean, this is something that should have been tested by now. 350 years and you still can't show me an experiment where it takes 4 times the fuel to move something twice as fast? Get real.
The goal of this video is not to convince anyone that this is the way the physical reality is actually working.
Well, I think that should be the goal, is to make a really persuasive argument with persuasive evidence. I don't know what the point of talking is if we're not going to convince anybody. Shit. Sorry, I'm just, I react, and this is what I do. So far, not so great.
But just to increase some understanding of the kinetic energy, both my own understanding and hopefully others as well. And
I just hope your included understanding is that Leibniz was in fact a religious kook. He did in fact publish this idea before Newton published his completely detailed explanation of the whole damn thing. So obviously he was doing it in a bit of ignorance, and in my opinion fooled entirely by the silly idea that yes, stuff falls 4 times the distance in gravity, but it's only getting 2 units of gravity, It's only 2 seconds. It's not 4 seconds in the gravity. So, I mean, continue. I'm just saying your history should be that de Charolais was in fact tutored by a Leibnizian who sued her for plagiarism. These are the facts that indicate, oh, this does lack a little credibility. It's as if we're going to talk about the Eddington experiment without including the fact that he says overtly in his diary, in his journal at the time, before he published his results, I wouldn't stake my life on these results because everything went so badly.
To give some perspective, mostly from the point of view of conventional physics. So yeah, I would be really interested in hearing your thoughts about this video, Gary.
Well, so far they're not very good thoughts, but okay, we have hope.
Let's start with Newton's second law. The conventional definition, or definitions, that you often find in textbooks, for example, is either force equals to mass times acceleration.
And he didn't write that. That isn't Newton's equation. Okay, so let's just make that clear. Newton said it's momentum over time. And obviously if the time is the total time of an interaction, it's the net time. It's a ratio otherwise. He's giving you the option of making it per second or net, total. You can do it either way. And if you do it with a total force, it equals the total momentum. Whatever the change in the total momentum is, that's exactly what the force is. So again, that's what I have drawn. You're supposed to explain how that drawing of the equation is incorrect. That interpretation of the equation is incorrect.
Or force equals to the rate of change in momentum, meaning the change in momentum divided by the change in time.
Well, why would it be divided by the change in time? That's a rate. There's no need to divide it by the change in time if you just know it's the force, the total force. Then there's no need to divide it by anything but 1. 1 would be the net time.
These two here are, of course, the same. To see why this is the case.
So this is going to be one of these unpleasant mathematical gimmick bullshit videos. Shit.
Let's first write this in a simpler form. So we get the change in mv divided by change in t.
What does you mean by change in t? There's no change in t. You can't change the time. The time doesn't change. It's either an amount of time. How many seconds was it doing it, this acceleration? And that's all you're finding is the rate of acceleration by dividing it by some unit of time. But there is no change in time.
And as we can assume that the mass of the object is not changing, we can take this m outside the thing that is...
So that's all he's going to do, this redundant mathematical gimmick shit. Where they go per second per second. Sorry to be insulting, but fuck this. We've been over this 7,000 times. You think you have a mathematical proof. I'm saying you have no physical evidence, and this mathematical proof is a distortion of what Newton said. Newton didn't do any of this. Show me where Newton did this to his equation. Show me where Newton made this dt dv bullshit. Show me that. Because he didn't. Because he would have gotten wrong answers if he did. Clearly, every single thing Newton did was considering the quantity of motion to be energy. He had no other understanding of energy than momentum. He never wrote an equation like this.
Changing. So we get m times the change in v divided by change in t. And this object here is of course the same as acceleration. It's the rate of change.
It's a change in your velocity. So again, acceleration isn't some special thing. It's just you changing the velocity. And what does Newton say? You want to change the velocity, want to double your speed? Well, you add double the force. That's Newton's overt words. You want to triple your speed? You triple the force. Clearly, a one-to-one relationship between the change in your momentum and the change in the force. So just quit doing this crap and saying it's Newton's physics, because it isn't. Oh, God damn. Disappointing so far. I'm really not interested in mathematical proofs, frankly. If you can't draw it, I can live without it. So try to draw your timed interaction. Show me how the acceleration took place and it's twice the acceleration, or it's a squared acceleration. Show me how that happens in a drawing.
Change in velocity. If you have high acceleration, it means that there's a large difference in velocity within some unit of time. And according to you, what Newton was actually saying...
No, what Newton actually did say, not according to me, according to the English translations, according to the one Dispar found, is Newton said, you want to go twice as fast? Apply twice the force. The two things are the same thing.
Is that if you want to go twice the velocity, you need to apply twice the force. And I guess that your argument is that this is somehow incompatible with this equation here.
I'm saying it's incompatible with your A. Your A is per second, okay? It's a nonsense. It's not a rational A. If your A was just the change in the velocity, that is a velocity number like 5 miles an hour, that's the change, just 5 miles an hour, then it would be fine. There's no problem. If you just make it a velocity, the acceleration is a velocity. It's a change in velocity. That means it is a velocity. It has to be a velocity. Just make the velocity bigger, make the velocity smaller. You have to add something called a velocity. It's just a velocity. It's not a squared thing. It's not a volume of velocity. It's just a velocity.
So let's take a closer look at that. First, let's assume that the mass is now changing. So now it's quite easy to see that if we double the force, we are also doubling the acceleration. And let's also take a look at what this means.
No, you're just doubling your total velocity. I don't know what you mean by you're doubling the acceleration. There's only one acceleration that doubles your velocity. Why am I doubling the acceleration? I only applied one acceleration to double my velocity. Let's say I just applied one acceleration. I pressed on the gas pedal. I went from 30 to 60. It's one acceleration. Why would I double the acceleration? Shit.
In terms of velocity. So here we have two objects with the same mass. To this object here, we are applying twice the force and thus giving it twice the acceleration.
I don't even know what that possibly means in this context. This is going to go one velocity, you're saying, and this is going to go two velocity. That's your argument? Okay, we'll agree. Two force to go twice the velocity of the other object that has one force. Obviously, I thought you were talking about from a standstill. I didn't know you were talking about comparing it to another object moving at half the speed.
And we are also assuming that both of these objects start at rest with zero velocity. And now it's quite easy to see that at each point in time, this object, where twice the force was applied, has twice the velocity. So, in this sense, you were correct about what Newton was saying. If you want to go twice the velocity, you really do need to apply twice the force. Of course, assuming that the duration of the force is the same. Because you could also...
Why wouldn't I assume that? That's the whole point of the t. If you're going to change what the amount of the force is, if you change the t, you're changing the amount of force. So, of course, I'm assuming that. I mean, the ingredients, you can't change the ingredients. You have a 50% flour, 50% sugar. Well, if you decide to double the sugar, it's not the same cake.
So apply the force, maybe the equal force for just a longer period of time to gain more velocity.
Yes, you can hit something with a 10-ton train going 5 miles an hour, or you could hit it with a 5-ton train going 10 miles an hour. Same difference. Yeah, that's what I've been arguing for 2 years.
But if the duration is the same, then you need to apply twice the force to gain twice the velocity. And this F equals ma is just another way of saying that, whether or not Newton ever used it.
I don't want to argue this, right? That's not what they're saying, okay? They're using F equals ma to square the velocity. So let's just not pretend that's not what they exactly do with their formula. They say F equals ma does equal 1/2 mv squared. They convert it into 1/2 mv squared. So don't pretend that's not what they're saying. Shit. If this is what they were saying, that twice the force equals twice the velocity, there wouldn't be an argument then, would there? Come on.
Word acceleration. Okay, then something about guns and bullets. Several times you've made the argument or thought experiment where we have...
Okay, just being fair cop. Okay, so fair cop, what was his counter argument? How did he defend 1/2 mv squared there? How did he do anything? He didn't do anything. He didn't point out how their math is rubbish, and he didn't point out how Newton's logic was solid. He didn't do either one. Well, he sort of did. I mean, he sort of said, yeah, Newton's right. But he didn't go any further than that in the sense that he didn't point out how their convoluted math is a pile of shit. Their per second crap.
A gun with relatively high mass, a bullet with relatively low mass, and an explosion applying equal amounts of force both to the gun and to the bullet. And the question is how...
Yes, well, let's just say, I mean, just it occurred to me this morning, so I'll just bring it up. Well, let's, see, we just don't have these tests. Maybe I can find this because people do a lot of ballistic tests. But how much velocity would the bullet lose if I just had a barrel? Open at both ends. How much slower would the bullet move? Because we're back to, it's really just what the bullet gave away argument, right? We're really talking about the fact that the event is happening on this nuclear level, so to speak. The atoms are being degraded and broken into little tiny pieces of energy, and little pieces of energy are going to push the bullet. But do they need the back of the gun? So you're making the same, I'm making a sort of like the argument with the rocket ship, where they basically, NASA knows it's better if the ground isn't in the way. The rocket has more thrust if the ground isn't in the way. They'd rather not push off the ground. It works better without the ground in the way.
Is it possible that the bullet gains so much more kinetic energy? Let's say the bullet gains 1000 joules when the gun gains only 10 joules.
That's not really fair, but we'll roll with it. I mean, it really is 1,000 to 1 by their definition, okay? So I'm just saying that realistically it's a really, really huge difference. It's not a 100 times. It's 1,000 times difference.
Even though the force was the same. Now, a simple answer one might give you is that when looking at the definition of kinetic energy, it doesn't depend only on the force applied. The force alone doesn't determine the kinetic energy.
Well, again, so what's the point? I'm not going to play that. The force alone, what are you talking about? It's an explosion. It has a certain amount of energy, light photons, so to speak. Those have to produce the energy. There's nothing else to produce the energy. So saying there's some magic fairy that produces the energy isn't going to do this conversation any good. I'm not buying that.
But this perhaps isn't explaining anything.
Yes.
So I have this thought experiment that hopefully would give some intuition, give some intuitive understanding on how the bullet gains more kinetic energy. So here we have the barrel of the gun. This is the bullet. And
all right, so let's understand that he's nearly not going to touch the real argument. So let me do the real argument that I've been doing over and over again just to be clear of what's being wrangled. And I've drawn this and over again. So this is what I want responded to, because this is the part where there is no conservation of momentum by their theory. Okay, springs don't conserve it, levers don't conserve it, guns don't conserve it. So it's just a fallacy that they believe in conservation of momentum, because they don't. Clearly they don't. Is this going to show up? Oh. Everything is broken today. I need the other camera. Nope, I need the other camera. Okay, and then I have to do this. And then I have to get rid of this, whatever the fuck it's doing. It's too bright. So we'll cut the gain down. Alright, that should work. Alright, so the simple example is, okay, I put 2 very light bullets in the gun. I explode it. Okay, I get 1,000 joules of energy. Okay, I put 2 very heavy bullets in. Okay, I get whatever, 2 joules. So we'll go with we'll go with the lesser amount. I should just make it a 1. It's 1,000 times less realistically. 2 things that weigh as much as the gun versus 2 things that weigh as much as the bullet. Right, so I have 1,000 going both ways. I have 1 going both ways. In this experiment, the explosion produced 2 total joules of energy. In this experiment, it produced 2,000 total joules of energy. The same explosion, completely irrationally impossibly different amounts of energy produced by the same explosion. Too silly. That's what I want you to explain. But anyway, go ahead. Do whatever you're doing instead.
just to make the visualization easier, instead of an explosion, let's use a spring, a compressed spring as energy. So when the gun is fired, the spring is released. It is pushing both the gun and the bullet with equal amounts of force. And
well, that's under some contention now. But anyway, go ahead.
As the bullet has lower mass, it accelerates easier. I hope you, Gary, also agree with this.
Yeah, it gains a higher velocity completely proportional to its mass. It interprets the same momentum, the same pressure, the same weight, and it interprets it by having a high velocity. Well, the big mass will collect a much lower velocity, but obviously it has a much bigger mass, so it's going to collect the same momentum. Yeah, so you're going to just prove momentum again. Kinetic energy is the subject. But anyway, okay, well, never mind. Sorry, go ahead.
So when the bullet travels some distance, the gun travels only a tiny bit to the opposite direction. And let's also decompress the spring like this. Yeah.
Yes, there's 1,000 times difference in their velocity, and there's 1,000 times difference in their mass.
And now it's quite easy to see that most of the spring was actually moving towards the bullet, to the direction of the bullet, whereas only a tiny bit of the spring was moving to the direction.
It's only because it yielded. That doesn't have anything to do with it. So again, you're broken the explosion analogy now, because now you're playing a game that somehow, because the spring extends in a direction, which you haven't proven, by the way, that springs actually do that, that somehow the direction the spring expands in somehow indicates it pushed more energy in that direction. When no, it's obviously a lighter object. It obviously went that way because it's easier to go that way. It has nothing to do with how much energy it's going to put into the two objects. Its center of mass is still its center of mass, and that's where it's expanding from. Its center of mass. Its center of mass is moving, but that's not a big deal.
Of the gun. So there's clearly some kind of imbalance, asymmetry.
Okay, so I mean, I don't want to, we could go into the minutia of the dropping the slinky from the building thing and the fact that, the slinky actually doesn't, the center of its mass doesn't fall. Okay, so I mean, there's lots of things you can do to show, but the fact is it's still proportionally pushing on both objects.
In the way the force was applied to these objects. So this might already suggest why the bullet gains more kinetic energy.
No, where did it come from? It can only be in the spring, so you're just saying, you've got to explain to me why when it pushes the bullets, okay, I put 2 bullets in the gun, it will fire them at 1,000 times the speed in both directions, and when I put 2 guns in, I only get 2 joules of energy. The 2 guns barely move. Explain how that is consistent with your kinetic energy theory, because all the kinetic energy, almost all of it, is destroyed somehow. I mean, All right, so I shouldn't have done this live video. See, I thought it was sort of a response to the actual arguments I was making and showing how those arguments were wrong. And he really hasn't shown that anything I drew was incorrect. He's just trying to make a rationalization for their nonsense. He's just giving me more of their crap to argue. Like, here's a crappy interpretation of what they're saying. Here, debunk it. No, your obligation is to show what I draw and explain where I made a mistake. That's what I'm looking for as a response video, is for you to take any one of the things I've said and show how that can't be true.
Or at least give some kind of intuitive idea about this. But what I think is also quite interesting is to think about what happens if we rewind this scenario. So what happens if we make things go backwards? So we have this bullet with its final velocity gained from the spring. It's now traveling towards the spring. And doing so, it pushes the spring, it's compressing the spring.
Right, it's adding pressure. The pressure of the bullet is now being conveyed to the other surface through the spring. And it'll take a little bit of time, but the pressure will show up at the other side, and the other side will start to move because of their sufficient pressure for it to absorb the energy. Not terribly interesting.
Spring further and further. Also the gun is doing some compression, but to a lesser degree, just a tiny bit. But the bullet is doing most of the compression work.
It's doing equal momentums. Their momentums are equal. This one is decelerating at the same rate that the higher mass is accelerating proportionally, just like a lever, for example. So I guess you didn't bother with the lever argument and the conservation of momentum. This high acceleration is being converted into a lower acceleration in the gun. There is nothing surprising about that. If we could do these, experiments perfectly, that is, if the Newton's cradle actually worked, okay, it would be kind of interesting because you could see all the energy from the bullet go into the gun. But a spring, that's not going to happen. The gun takes time to absorb the energy. It needs more time to gain its velocity, all right, because it has a much more matter to push. And the spring isn't going to give it that time. The spring is going to fully compress with all of the momentum that it hasn't lost. That is, the more I yield, the less the thing can fly back. The more my side yields, the less the rubber ball bounces off. So obviously I'm using some of the energy, but if I can't absorb the momentum in the short amount of time I have, then I have to reject it in the sense that the spring will start expanding in the opposite direction and push the bullet. Whatever. I mean, if we did this ballistic pendulum, okay, this is essentially, then you use clay or use some other substance so it isn't elastic, so it absorbs the bullet's momentum and puts it into the larger mass. And then you'll find out that, yes, momentum is conserved and kinetic energy is wiped out entirely. The heavy thing moving slow has no kinetic energy almost, and the fast little thing has a ton and ton of it, even though it's the same momentum. So we're all the way back to the same argument. You're saying you can do work without using something's momentum. I'm saying it's impossible to do work without using momentum. Something has to provide you the momentum energy. Something has to provide you the energy, and in any case of a moving object, the energy is its momentum. It can't do work and conserve its momentum. Work is the use of momentum. I mean, I know Veritasium just made a video where he's playing with the word entropy, but that whole conversation about the fact that we gain nothing from the sun. We're only using the energy from the sun for a little period of time. And the only energy we get from the sun is the stuff stored, okay, in the carbon, okay, that we're throwing back into the atmosphere. But other than that, the Earth is at equilibrium. It's gaining nothing from all the light hitting it.
And doesn't this fit quite nicely with the idea of kinetic energy?
I don't know how the hell does it fit nicely with anything? I don't understand. You conserve the momentum, and you completely annihilated all the kinetic energy. I mean, if you absorb the bullet, like I said, if you don't have the spring. If the spring is going to compress and then it's going to shoot the bullet out with a certain momentum, what are you going to say then? Well, because it was hitting this heavier object, it went away with twice the velocity, twice the momentum. Is that going to be your argument? So, you're not even up to date in the sense that their theory is that if I make this surface heavy enough, the gun heavy enough, the fact is, and I put this spring in here, I'll end up with twice the momentum in the gun. Somehow, the bullet comes in with a momentum, and the gun will have twice as much momentum. And the bullet will leave with 100% of the original momentum. That's their theory.
At least I think that kind of the core idea of kinetic energy is that objects with higher kinetic energy can travel further against some opposing force, against some kind of pressure.
You have to debunk momentum, frankly. This is retarded. I'm sorry. I don't want to. Clearly, in any exchange between two objects that have a different mass, you cannot possibly ever, in a rational way, conserve both the kinetic energy and the momentum. My argument to you is whatever you're not conserving isn't real. If you aren't conserving it, it's not real. Conservation laws are incredibly important. So you're basically saying you can poof energy out of nothing and you can destroy it into nothing. I'm saying that's not possible. So you have to pick one of these theories. They're not compatible theories. You either believe momentum is the nature of the universe, runs on it, or you believe in this, whatever that is, this poofy energy.
Assuming they don't bounce or explode or anything like that. And actually this is also an answer to the question, why don't they use bullets to take down buildings? When you shoot a bullet towards a building, what happens to the bullet is that it either just explodes.
Oh, please. Yeah, exactly. It hits the matter with its energy and it has to transfer it to the matter. It can't just make it go away. It has to actually hit the matter and transfer its energy. Exploding is a pretty powerful thing to be doing. Exploding doesn't mean you didn't use your energy. You didn't move particles. You didn't break things. Of course, that's exactly what it means. Shit.
Or it bounces, or it drills a small hole to the material of the building.
Indicating it's a small amount of energy then, huh? I'm just saying, you can't have it both ways. It's explosive, yet, it just drills holes. That's all it does. Come on.
Which really isn't useful when trying to take down the whole building. And that's why they are used.
You have to talk about this as if these are real atoms. You know what I'm saying? I mean, come on. You're saying that one atom moving 1,000 miles an hour has 1,000 joules of energy, so to speak. And then you're saying that 1,000 atoms moving 1 mile an hour has 1 joule. That's your logic. I'm arguing that no, there's no distinction. They're both going to apply the same total pressure. And so if you spread the 1,000 pounds by the one atom over the same amount of surface, it's going to add up to exactly the same thing as the one atom pushing with 1 mile an hour. It's all going to turn into the same thing. It's the same amount of currency. Whether you're throwing nickels or you're throwing dimes or you're throwing quarters, it's the same amount of money. So anyway, this is just, I'm sorry, this is a little non-responsive, okay? I mean, I've drawn better diagrams than this, and I've pointed out that, okay, if you want to just say our belief is that we just imagine the energy and that's all we have to do, we don't have to account for it. We really don't have to explain how the atom hits another atom and another atom and another atom, and somehow it just makes more atoms move. So the bullet somehow, even though it has 1,000 less atoms, it somehow makes 1,000 times more other atoms move.
Using these heavy wrecking balls instead, even though the kinetic energy might be lower. But the wrecking balls are more suitable for the job. Another similar example.
There's no science there. You didn't make any more suitable for the job. That's why they use dynamite, actually, right? So you're saying it's more suitable to use a wrecking ball. No, they use dynamite. So, C12 or whatever. So what are you talking about? We're not really talking about a strategic. We're just talking about the fact that what provides the most bang for your buck energy-wise. I'm sorry, this is just unresponsive.
Might be that if you have a person running towards you and you want to stop that person, you might take a small particle, very small particle, shoot it with very high velocity. The particle might, for example, penetrate the cell of that person, maybe cause some DNA damage or something like that. So the kinetic energy of the particle would go into breaking some chemical bonds. Even though lots of energy was used, it wasn't really used.
So you're talking about momentum again. Again, all the contact energy is all momentum. So again, I don't know how you can make this argument that somehow the 8-pound ball makes pins move more. It can't make them move more. It can only make them move less. Less pins move more velocity. So I've already drawn that diagram. The 8-pound ball loses more energy more quickly, but over the long term, the 16-pound ball is more durable and is producing more energy after it's hit a few pins because it gave less away to the first pins. So again, you're not really addressing my point. Well, you're not. This doesn't show me where does this extra kinetic energy come from. I have two examples: a spring pushing a heavy thing, a spring pushing a light thing. You're saying when it pushes the light thing, the spring has 1,000 joules of energy stored in it. When it's pushing the heavy thing, it only has 1. I'm saying bullshit.
Useful in stopping that person. But you could also take a stone. Heavy stone, throw it to the face of that person, and even though the kinetic energy might be lower, it probably is still more suitable for the job, for stopping.
Whatever. We're not talking about suitability. We're talking about the movement of atoms. They have to have you hit them, they have a velocity. You have to conserve whatever this is, all right? And you're not conserving the momentum anywhere. You're just saying, I guess, make up a fake amount of energy, and I won't show you an experiment where it proves any of this crap. So what the fuck's the point of it? Unless you're going to show me some experiment where you proved where all this energy went, you got nothing. And you're certainly not going to prove to me that the lever doesn't conserve momentum, and then you're not going to prove to me that if it did conserve momentum that I didn't create free energy with it, because the fact is I can make the 10-ton train going 5 miles an hour create a 5-ton train going 10. And if I can do that, your kinetic energy theory can't be reality, because that would be free energy and we'd all have free energy machines. So obviously there's a simple answer here, and you're evading the simple one, okay, and talking mumbo jumbo about what you say it has. But you can't show anything does this. The big wrecking balls work because they have the same energy as the bullets, and yes, it's strategically more sensible to fracture buildings with heavier weights than with light weights. But the fact is you could do it with bullets. It's just you're not going to gain any of this 1,000-to-1 efficiency. There's no point. So just say you're defending the idea that the gun you don't have to conserve momentum. So just say the words. But you can't do both. The gun and the bullet can't be conserving momentum. It's impossible if one of them has more energy.
That person. Okay. You also had this extension to this thought experiment where we have two guns facing each other and two bullets in this, what you call a zip gun, I guess. So basically a tube, two bullets, and an explosion in between them. And I guess your understanding here is that since the gun in the first scenario gained only 10 joules of kinetic energy, now both of these guns would gain 10 joules or 20 joules in total. And the bullets here would gain 2000 joules of kinetic energy in total, even though the explosion was the same. So obviously there seems to be some kind of contradiction, and I also think that obviously this is not what would happen.
Okay, so that's great. I don't know how you could imagine something else would happen, but okay, great. But you won't have any experiment. You won't have anything to show me. You're just going to say, oh no, that doesn't happen. You put heavy bullets in the gun, somehow the heavy bullets violate conservation of momentum and somehow catch up to the fast bullets in terms of their speed and their momentum. So again, you have to violate momentum. You have to violate the conservation of momentum to create any other scenario here. But okay, go ahead. Let's see you defend this.
Especially if we are assuming an ideal explosion, so all the energy of the explosion goes into moving these objects, then the kinetic...
I don't even care. Make it a really unideal. We have 1,000-to-1 difference, okay? So frankly, if you want to say the guns fly apart and this flew over there and this did that, I don't even care, because frankly, okay, even if it was 10% less efficient, 20% less efficient, 60% less efficient, it's 1,000-to-1 difference, okay? You're still way out of bounds, okay? You still really haven't conserved the momentum. So I'm just saying, yes, your any contrivance of the fact that the guns don't absorb the energy as well as the bullets can mean almost nothing, because you have 1,000-to-1 difference to make up.
The energy of the guns equals to the kinetic energy of the bullets, meaning that the guns here would gain more velocity than the gun in the first scenario, basically because there's no light object here stealing the kinetic energy and
stealing it, he says. All right, so you don't believe in conservation of momentum. That's all. That's okay. Okay, so you're saying that the momentum of the momentum the explosion can produce can be different. That somehow the little bits flying off that all have momentum from the explosion, the little bits can somehow give more energy, okay, a lot more, A lot more, depending on what they hit. So no conservation of momentum. That's your argument. Okay. I mean, that's not what physics says. Okay, so why are you arguing with me? If you don't believe there's conservation of momentum, why don't you inform Professor Lewin of it when he said nature can't finagle momentum? Why don't you point out that sure it can? We do it all the time.
The explosion to spread out into one direction. And the bullets here would gain less velocity than the bullet in the first scenario, basically because there's no heavy object here. Redirect.
Again, it just couldn't matter, the heavy object part, right? The energy is trapped between the two things. So even if you say the guns are moving so slowly that they're not absorbing the energy, quickly enough, which is still bullshit, I'd argue, because the explosion really happens so quickly, and the motion is quick enough, okay, that it's going to expand before any of those reflections could possibly take place. And so, again, the most your reflection, let's say a reflection did take place, and you're saying I gave 2 this way and 2 that way, even though I started with only 1 little bit moving. Even if you doubled it, right, you still aren't anywhere near 1,000, right? 1 times 2 is 2. You haven't gotten very far. I mean, 2 to 1,000 isn't much better than 1 to 1,000. So again, what's your explanation? The energy died? The kinetic energy died somehow when the guns are facing each other. Somehow the kinetic energy just died. Even though it's in the scenario, basically, it's a sealed. There's one gun was inside the other. There was no place for the energy to escape. It has to hit this gun or it has to hit that gun. It doesn't have some other choice. And if it somehow isn't going into it, then it has to reflect. And if it reflects, it has to hit the other gun. It doesn't have a choice to hit something else. So you're just basically saying somehow the energy got tired or something and it couldn't get into the guns. I mean, it's not a reasonable argument. And again, it's premised on you saying I don't have to conserve the momentum.
Directing the explosion to the direction of the bullet. So, at least to me, this is quite intuitive and I don't see any contradictions here.
Okay, so I'll point out, you're first overtly rejecting what standard physics says is a rule, almost. They don't really say, well, they do say the law of conservation. They call them conservation laws. And you're saying in this closed system, it's a closed system, you don't have to conserve the momentum. Well, I'm overtly saying to you, okay, then argue that with conventional physics, because they say you can't do that. You have to obey physics girls' logic. The 5-ton train hits the 10-ton train not moving. So you have a 5-ton train going 10 miles an hour. It hits a 5-ton train, sticks to it. And then they leave with the momentum conserved. And half the kinetic energy disappears. That illogic is what you're stuck with. Okay, you have to explain where it went. And if you start saying something deformed or something heated, then I'm going to say, you heated it without using any momentum? That sounds like a fairy heat. Gremlin heat.
Then we'll talk about acceleration and fuel consumption. So you have made the point that according to kinetic energy theory, you would need 4 times the fuel to gain twice the velocity. And
right, and let's understand that is exactly opposing what Newton said in his second law. So let's not use some second law logic that Newton somehow agreed with this crap, because he overtly said, no, that's not what it requires. Twice the force, twice the velocity, twice the momentum. Okay, so let's just understand, there is no 4-time crap in anything Newton said.
So say that this never happens, this is not reality.
350 years later, yes, you have produced zero experimental evidence in the records of humankind. There is no fucking video, no paper, no anything you can show me indicating this really happens anywhere.
And I would say that you are partly correct here. It depends on the method you are using to accelerate. When it comes to acceleration, there are basically rockets and cars. So what rockets do is that they use the chemical energy of the fuel to push out part of the fuel mass into the opposite direction, and thus giving the rockets.
No, they actually shoot springs. So you don't even have that quite right, okay? So the energy is in the chemistry. It is a compressed spring, okay? And what they do is they have a whole bunch of springs in a tank. So there's energy in the fact that they push the spring out, the hose. But what they really are doing is expanding the spring, okay, in the nozzle of the rocket. And its expansion is another jolt of energy. So not only are they losing energy from their hydrogen tank, okay, it's depressurizing, and that's a overt little bit of energy. But the big pile of energy they're getting is making the water molecules. That's where they're gaining the huge amount of expansion pressure. And it's that expansion pressure in both directions that they're taking advantage of. I mean, frankly, the whole exhaust you see, the flame flying out of the rocket engine, is an example of a huge waste. There's a big pile of energy going nowhere. A big pile of it. It would be better if they could capture all of it.
Some thrust. Whereas cars, they use the chemical energy of the fuel to push against some immovable object. So the tires push against the road, and the road isn't moving anywhere, practically speaking.
Whatever, this is just absolute. Sorry, you're not going to go anywhere with this theory, okay? Because on the chemical level, it's the same expansion. You're just talking about little explosions. Little explosions create pressure. Both vehicles are using the pressure to move. One of them has a more direct pushing force, and the other one's using cylinders, okay, to control the pressure. But it's the same exact thing.
And I would argue that the fuel consumption between these two methods is different.
We're just talking about the relative comparisons. We're talking about going from 30 miles an hour to 60 miles an hour. So we don't have to worry about these relative things. Okay, the inefficiency is the same inefficiencies. Okay, the inefficiencies of the engine are pretty much the same at 30 miles an hour as they are at 60 miles an hour. It's kind of silly to say, yes, you gain a little bit from the heat. Okay, it makes the engine a little more fireable, but you also have downsides to that. So you could go through all the things, the tires getting hotter, the tires getting softer. You could argue lots of little details, but fundamentally the two cars are the same efficiency in terms of the engine's ability. And it's not inefficient enough to change your 2 to a 4. So that part you're just not going to show us.
And let's take a look at why that might be the case. So here we have a rocket in space outside of gravity. Let's say it has a mass of 10 and it starts at rest with 0 velocity. Then it shoots out some unit of fuel with a mass of 1 and velocity of 10. I put a minus here just to emphasize that
I don't know what use this is. That's a momentum argument, okay? That's a Newton's third law, conservation of the energy. So you're stuck. I don't know how are you going to prove kinetic energy with that example? Because that example is exactly opposing it. It's all momentum.
Direction is opposite from the point of view of the rocket, but that really isn't that important. What is important that the rocket gave this unit of fuel some change in momentum, and thus the rocket also gained the same change in momentum to the opposite direction. So it gained 1 velocity.
Yes, undeniable. So how are you gonna say that it's going to take 4 units to go faster? I mean, I don't know how you're going to do this. Used one unit to gain a certain velocity, momentum. You're going to use another unit, get the same increase in your momentum. You're not going to be able to change that. Newton was right.
Note that here I'm not taking into account the loss of mass of the total rocket. So
yeah, because it could be totally negligible and meaningless. Okay, if I have 400 tons of fuel, the fact that I just lost 3 pounds ain't gonna matter.
the total mass of the rocket is the rocket itself, but also the fuel that it's carrying. And now it's shooting some of the fuel out, so there would be a decrease in mass, but just to keep these numbers simple and keep the math simple.
Well, yeah, there's no point in doing the what they call the rocket equation, right? Or yeah, there's no point in doing it's an insanely long, complicated mush because everything is changing all the time, and so there's no point in doing all that crap.
I'm not going to take that into account, but let's get back to that in a moment. Next,
You're not going to change the facts, okay? And the fact is, the faster I go up into gravity, the less gravity I have to oppose, and that's the huge efficiency. There's nothing else.
rocket shoots out another unit of fuel, again with the mass of 1, and as the change in momentum is still the same as with the first unit of fuel, this unit of fuel has a velocity of 9, because it was initially traveling with a velocity of 1 to the direct.
Oh, this relativity crap is just a pile of crap. So just playing this game that it's we're changing how fast the fuel is going. It's just too silly. We know the fuel is going insanely fast. All right, so it's not doing this 10 velocity thing. So this is just baby talk you're playing here. That the speed at which this rocket is moving has something to do with the relative change that you're making. You're making a relative change, and the relative change is the same.
Of the rocket.
The rocket's not going to release the energy at a slower speed as it goes faster. That's not going to happen because the speed of this expansion is, zillions of miles an hour compared to what the speed of the rocket is. So this is just baby talk, frankly.
But still, the rocket gains the same change in momentum to the opposite direction. So now it's traveling at a velocity of 2.
No, it's only doing 19. If what you said is true, okay, that somehow the fuel is only leaving the rocket at 9, then no, it isn't. Okay, then it's only got 19. You have to conserve the momentum. So if you're going to make this argument that somehow the fuel knows that it has to leave the rocket at a slower speed, relative to the rocket, bullshit. I mean, obviously, the fuel doesn't have to go as fast. If the rocket goes faster and faster and faster, the difference between the first piece of fuel and the speed of the second piece of fuel in terms of where it will be in space will be different. But it's like photons, Their spatial difference will be their spatial difference, period. But they're going the same speed.
So, based on this, doubling or using twice the fuel would lead to twice the velocity. And if we took into account the loss in mass of the total rocket and the fuel it's carrying, we would see that acceleration would become easier, and thus twice the fuel would actually lead to a bit more than twice the velocity.
Look, we're talking about 4, okay? So you're not going to get anywhere close to 4, okay? 2.016 is not anywhere close to 4. Shit.
But things are a bit different when the object is pushing itself against some immovable object. So here we have a thought experiment where we have 2 immovable walls with some springs attached. And here's our object, our ball that we are going to accelerate. So let's load our ball and let the first spring decompress, giving the ball some acceleration. And here we engineer the experiment somehow that the ball can pass through the second wall.
I'm not even going to listen to this, right? What the fuck are you talking about? Come on. God damn it. I mean, what? I don't want to do thought experiments about walking through trees. No, thank you.
And just when it's in front of the second spring, we let the second spring decompress, giving the balls up.
What are you talking about? Decompress? How could you compress it? What are you talking about? This is ludicrous. It goes through the wall and somehow compresses the spring this way. I don't know what you're talking about. Too silly. If you want to say that the springs are going to give it more energy and then you hit it again, then make a water wheel or something and say you're going to hit it once and then you're going to hit it a second time. Why don't you just make a water wheel? Okay, make a water wheel and have one here and then one here, and they're both spinning. And the thing gets hit by the first water wheel and gets pushed, and then it gets hit by a second water wheel and gets pushed. Well, yeah, obviously a sensible thought experiment proves that, yeah, it's the same push. Yeah. I mean, obviously water wheels turn very slowly, so again, you have to recognize that the second one's not going to be able to push it at twice the velocity because it's not going to be capable of moving that fast. It's not moving fast enough.
Additional acceleration. And the question here is, do you think that both of these springs gave equal amounts of acceleration to the ball?
They either conserved momentum or they didn't. So yes, springs can expand very fast, springs can expand very slow. So they're completely adjustable. I can throw something with the same momentum. I can throw a heavy thing into the spring, okay, and it'll bounce back with the same momentum I put in. And I can throw something light, fast, and it will adjust and produce the same thing. Now the compression of the spring was exactly the same in the two circumstances. I compressed the spring exactly the same. And the spring can, in fact, with that spring compression, I can either make the light ball go fast or I can make the heavy ball go slow with that same compression. So of course the second spring can expand quicker and give it a higher velocity. It doesn't care. It's already going 20 miles an hour. The spring can go 100 miles an hour. It's not going to have any problem pushing on the object. The spring can expand much faster, okay, than the ball's going to end up moving. So no problem getting the energy in.
Was the change in velocity the same with both of these springs? Because that would certainly indicate that twice the fuel, or twice the spring energy in this case, would lead to twice the velocity.
Yeah, not 4 times the velocity. So again, you're even making my argument in a backward way. You're making the point that, well, the worst case would be the spring didn't get its energy in, so the ball goes less than twice the velocity because the second spring has a little more trouble. How is this 4 times the energy again? I'm sorry, I'm not getting it.
Now, I don't think that's the case. What I think would happen is that both of these springs would apply equal amount of force to the ball. So the push would be the same in terms of force. And what would happen with the second spring is that as the ball is already moving here, it already has some velocity, the second spring decompresses faster. And so...
Yes, with less pressure. I mean, per time, it's more pressure, So that's all it can do. It can just hit things in a unit of time, and it can push something slow or it can push something fast. I mean, obviously, the amount of pressure it takes to move the mass is the amount of pressure it takes to move the mass, to add velocity. So you have to accelerate it at the rate it can accelerate. You can't accelerate faster than it can absorb the energy of acceleration. That's why, heavy things are harder to move. That's why the Newton's cradle doesn't work, because it can't do the conversion. The point is, springs do the conversion. Springs convert the pressure, the rate of acceleration, to the rate that the object can absorb the acceleration. The spring does the conversion. The same spring compression will produce the ball with the same momentum. It'll produce a light ball with the same momentum it gives the heavy ball. and the same momentum went in. It's conservative of the momentum.
It applies the same force, but for a shorter period of time. And at least to me, that means less acceleration based on the Newton's second law.
All right, so that isn't Newton's second law. That's just a lie. Okay, blah, 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 blah. Newton clearly said twice the force, twice the velocity. 3 times the force, 3 times the velocity. He didn't see any of these gigantic problems getting the energy into the object or any of that kind of crap. He's saying there's an applied force. The spring either uses its force and applies it, or the spring fails to put the energy in, and the spring oscillates and wobbles and does all kinds of stuff because it wasn't able to get the energy in. But there's no real other choices here. The energy has to go somewhere. It doesn't go nowhere.
And
you're not even getting the fact that, yeah, if this, you know, your theory basically says that when I launch this object with the spring, you know, well, there's no point in arguing it, but you have energy going in the opposite direction.
I did some calculations. I'm not showing the equations here because they are a bit messy. Maybe I'll put them in the description or something like that. But based on my calculations, if we have a spring that accelerates the ball from...
All right, so I'll just say, for the sake of argument, in 350 years, you could just show it. You know, show me something taking 4 times the fuel. So go ahead and show a real world experiment. I mean, every day we run things at 30 miles an hour and then we run them at 60 miles an hour. You know, every day we up the speed of something to twice the speed. All kinds of things all over the goddamn place. I'm saying, oh, please, just show me. Show me your device that is so inefficient. And that's about all you could do, is show me something insanely inefficient. You know, something that gets burning hot as you make it go faster. Well, that wouldn't be 4 times. Then you can make the argument that, yeah, the heat is part of the energy, being the waste. So besides showing something like car wheels spinning on the ground or something, what are you going to show? I mean, you're frankly hopeless. You're not going to show it taking 4 times the fuel, because if it happened, we'd have a video of it already.
0 to 1 velocity. You would need in total 4 of these springs to achieve the velocity of square root of 4, which is 2, which is twice the velocity in comparison to just 1 spring.
I'm sorry, that just makes absolutely no sense. You just conceded that it had almost twice the velocity, and now you're saying it doesn't have anywhere near twice the velocity after the second spring, and after the third spring it still doesn't have twice the velocity, and somehow it needs 4 springs to get twice the velocity. I'm saying that's just bullshit. You made up all that crap. Let's see. I mean, obviously, if I swing a bat at 90 miles an hour, the fastest I can make the ball go is 90 miles an hour. I can't make it go more than 90 miles an hour, right? It's as fast as the bat's going. I hit the ball with the bat, and the ball's standing still. I hit the ball with the bat. I can just make it go 90 miles an hour. I can't make it go faster than the bat's going. That's a limitation of the bat. You know, and again, the Newton's cradle doesn't work. So, you know... Well, the ball is elastic, so it will go away a little faster, actually. Somewhat elastic. Let's see, there's got to be a better analogy. I'm just saying, if the ball's already going 90 miles an hour and my bat can only swing, 90 miles an hour, I can't add energy because I can't hit it. I can never catch up to it, so I can't add energy to it. But these springs can catch up easy. Okay, this experiment is, you're saying, can I use a spring to fire a bullet? No, I can't. Can't be done. And it wouldn't matter how many I lined up, I still couldn't do it. Because the spring never can catch up to the bullet. So I can never release it at a time where it's going to hit the bullet, because it can never catch the bullet. So I can't add energy to something going faster than I'm going, because I can never even hit it.
So Here in the calculations, I just assumed that each spring applies the same amount of force to the ball, but the duration of the force is shorter.
It's silly. There's no duration of the force is shorter. The force is an amount. That's already a total, has the duration built into it. The force is the duration plus the pressure. That's it. That's what the force is. The force is the weight applied over a period of time. That's the force. So you can't segment the force and say the force is the time or the force is the pressure. No, the force is the combination of the two.
Because of the higher velocity at each spring. And
I mean, if I hit something very, very quickly, so quickly, that there's no duration to the pressure, it's, it hits it hits like the first cell on my skin feels the high pressure, and that's it. And it just dissipates through me. It's less force. And the longer I let that impact happen, the more cells it disrupts and the more stuff that can happen. But if I only hit one atom, I'm not going to be able to do too much damage. I mean, duration can be understood as just volume. In a way, duration is the opposite of surface area. I mean, the correlate to surface area. Duration is like surface area. The smaller the surface area, the higher, the disruption, the velocity. There's no other way to say it, really. You have to go back to mass and velocity. You have to go back to the number of atoms and how much motion they have. And we're back to Newton's quantity of motion, and that's all there is. 1,000 things going 1 mile an hour has the same quantity of motion as one thing going 1,000.
Of course, this is perfectly in line with the kinetic energy theory. So yeah, that was it.
So
would really like to hear your thoughts about this, and
300,
from other people
my
as well.
thought is 350 fucking years, the whole industrial revolution, and you don't have one single video showing it, the guy pouring 4 times the fuel in to go twice as fast. I mean, come on. This is just rationalizations.
Misunderstanding something or making some mistake.
No, if this is how you're going to argue with some completely bizarre, non-mechanical, not real-world experiment, that you're going to predict the outcome of some non-real experiment, yeah, that's kind of bullshit. So if you can't even convert it into something like, a gun inside of a gun is realistically buildable. This isn't realistically buildable, whatever the hell this is.
Okay.
Ugh. So that wasn't very much fun. I thought that would be a lot better than it was, and so I'm disappointed. But nothing new there. Okay. Draw a time versus velocity graph. Oh, isn't that fun? Oh, gross. They're the same thing. Again, you're let's do a distance one. Why don't you do that one? Yeah. Velocity by distance. Then you're basically, multiplying a cause times its own effect. All right, so let's see. Not too much spoken in the chat, which is fine. Let's see. How is gravity related to time? It's like rain. So you say, how is rain related to time? Well, the more time you sit in the rain, the more rain hits you and the wetter you get. That's how they're related. Let's be real. Would you fight Elon? I don't even know what that even means. He's fat, dumpy, and stupid, frankly. He'll probably punch himself in the face. He bought Twitter for $37 billion, was it, or something? I mean, come on. I don't even know. I mean, he probably blows his nose when he's supposed to be wiping his ass. I mean, shit. All right, so maybe we're done, right? I'll just see if I can actually get that composite window to work. Little chat window. It doesn't appear to work. Let's see. This should be it. Taking a chance. Let's see. I'll make it. I'll hide it first and then do it. Yeah. I don't think I have anything else on my computer that could get me in any trouble legally. Didn't show up anyway. Interesting. Maybe it has to be here. There it is. Alright. So we'll put it up a little higher so we can see it. Alright. So we'll see if there's no chatters, then we'll go home. And such. So yeah, so I'm probably going to just make, like I said, just make these videos over and over again until somebody actually makes an argument explaining why anything I said in the video is incorrect. So he did say I'm incorrect to think that the 2 heavy bullets and the 2 light bullets in the same gun, same zip gun, will not conserve the momentum. So he's saying you don't have to conserve momentum. So we have at least a statement by him. I'm saying you do have to conserve. The explosion creates a certain amount of momentum, and you really just have to deal with the little bits flying off, and they all have a destiny and a pressure and all that crap, and you have to account for them. They don't disappear. They don't go anywhere. Their energy always moves through the universe. There's no other place they can go. They have to hit something. You have to explain what they hit. You can't pretend them out of existence. That would be my counter argument to that. But yes, realistically, if you want to say you don't believe in conservation of momentum, then we can just agree to disagree or whatever, and I'll just say you should be arguing with regular physics because they do believe you do have to conserve it. Even though it's nonsensical. I mean, don't get me wrong. I mean, obviously it doesn't make any sense for them to say you have to conserve momentum and then to say kinetic energy is real. Because every single time you have a collision between 2 uneven masses, you have a real dilemma because you're going to have to destroy a bunch of your kinetic energy. You know, where the masses stick to each other especially, because then you just make them heavier and slower, and you automatically have to lose all kinds of kinetic energy. And physics is okay with that. I don't know why they're okay with it, but you know, Professor Lorenzo, he says you can something. He doesn't say finagle, but you can something kinetic energy one way or the other, but you can't finagle momentum. So he's conceding that this kinetic energy stuff just poofs into existence and poofs out of existence. But they'll make excuses, like the physics girl, you know. Oh, the cart's deformed, and there was sounds, and all kinds of things happened, and all kinds of things moved. Well, no, there's no evidence any of that happened. And on top of the fact there's no physical evidence any of that happened, there's no rational evidence that that could possibly have happened, and yet the momentum still went into the train. It can't do both things. It can't knock a piece flying off in a direction and still have the energy that it took to knock the piece off in a direction. You can't do that. Nonsensical is what that is. Alright, so let's see what the view numbers are here, and I'll just toddle off. Let's see. We have 5, so that's pretty bad on a, it's a Sunday. I don't know if I must have made it. Well, yeah, I didn't do too many live videos on a Sunday. That is true. So anyway, pretty dismal, so we'll say enough of a video. So thank you for the response. I frankly don't think you debunked anything I have argued happens. You didn't show any experiment showing that momentum doesn't have to be conserved or any of that kind of crap. So I'm saying it's fairly useless. I mean, obviously it didn't change my mind about anything. I'm not persuaded at all that your rationalizations and fake thought experiments have anything to do with reality. And clearly I don't think you're correct that I don't have to conserve the momentum of an explosion. An explosion has a certain amount of power to it, like a 10 megaton bomb. I can't make the 10 megatons not 10 megatons. It has to melt some rock, it has to melt this, it has to do that, it has to move the atmosphere, it has to conserve its momentum. You can't undo its power, okay? There's no container that undoes its power. The container has to absorb the energy. It has to be changed. You can't stop the change. It has to change other atoms. It has to bang into them, move them. They have to dissipate the energy into the entropy. It has to take the energy and move it into entropy. It has to migrate it to some other location. The energy can't not migrate somewhere. All right. And by migrate, you can also store it. You can use the pressure to compress something and store the pressure. But it has to go into storage or freedom. Those two things. It either goes, it's either liberated or it's put in a container and trapped. You either put the energy in a trap or it's liberated. There's no killing. There's no destroying, and there's no creating. You either trap it or you free it. The birds are either free or they're in cages. Can't make them disappear. Alright. So that's probably enough said. So till the next time and such, that be it.